12. And then I look at its isomer. Then I look at the other isomer. Oh, well, for now let's just 12. So all of those compounds are C5H12. Let's call them A, B, and C. So the isomers of C5H12. They're constitutional isomers. If I asked you to rank them in terms of boiling point, and to rank them in terms of melting point. Now, if you remember, when we looked at a series of alcohols, their melting points and boiling points went in the same direction. They went up or down. If I looked at the amines, we looked at one propylamine, at one propanamine, at the secondary amine, the tertiary amine, as the melting point went, so did the boiling point. If I ask you to rank those in terms of melting point, or boiling point, the highest boiling point is A, followed by B, followed by C. That's peculiar, because if I look at the nature of the bonds, those are all van der Waals bonded compounds, they're hydrocarbons. I look at the mass, and they're the same, they're isomers. And on the face of it, I might have thought the number of bonds was the same as well. So I'm puzzled as to why there's a difference at all between these. What's even more puzzling still is if I look at a melting point, the highest melting point is C. Right? The highest melting point would be C, followed by B, followed by A. So I've got a mystery. I've actually got two mysteries. One, we've looked and spent a lot of time exhaustively on the impact of the nature and number of the bonds and the mass of the molecule dictating physical properties, melting point and boiling point included. And here I am with van der Waals bonded compounds having the same mass, and yet there's a differential in melting point. There's a differential in boiling point. And the direction of boiling point and melting points are different. Something else is at play here. And the question is what? Those molecules have different shapes. And let's see how that plays out. That molecule is long and stringy. The neighboring molecules might look like that. Which means there is a large surface of interaction between one molecule and its neighbor. A large surface of interaction. More areas for bonding to occur, for van der Waals bonding to occur. More opportunity for van der Waals bonds, more van der Waals bonds. But if I look at that molecule, which basically is a tetrahedron, right? That molecule really, in a sense, feels like a sphere. So the interaction between that molecule and its neighbor only exists on that surface. But that's much less than that. So although the nature of the bonds are the same and the mass is the same, the surface area of contact between one molecule and its neighbor is not the same. So fundamentally then it feels like the amount of bonds, in a sense the number of bonds, is less in a spherical molecule and more in a long, stringy, unbranched molecule. So as a rule, unbranched compounds have elevated boiling points. Compact spherical molecules have depressed boiling points. Right? So there's more opportunity for bonding, for intermolecular bonding, over long, stringy molecules than there is in spherical molecules. There's another sort of subtext to this. Long, stringy molecules can do, so that in a liquid phase in particular, they have, we're talking about boiling points, so this is a liquid phase. stringy molecules swim past each other, and they often entangle. And as you're boiling, remember you're lifting molecule by molecule. So really what kind of has to happen is you have to kind of untangle them and then boil them. So there's energy required to do the untangling, right? So there's that component to it. The bigger one we talk about is the greater surface area for interaction. And therefore what is functionally more van der Waals bonding, more bonds to overcome, higher boiling point. But that's not happening in the melting point scenario. In fact, you know, it's exactly the opposite in the melting point scenario. So what happened to my argument that, you know, there's more surface area here and whatever? Well, we're doing two different things in a sense between boiling and melting. In melting, what are we doing? We often describe the solid phase as having something resembling a lattice, right? So in addition to mobilizing the particles, and by all means, more interactions, more bonds, more energy I pay. But beyond that, I am disturbing a lattice. Well, lattices have an inherent stability associated with them. Nature likes symmetry. So which particles pack better? Soccer balls or hair, right? Spherical molecules simply pack better than long stringy molecules. Long stringy molecules do not pack as well as spherical molecules. So when we are doing melting, in addition to breaking the bonds between the molecules, I am disrupting a lattice. The lattice associated with spherical compact molecules is more inherently stable. If I want to destabilize it by melting, I have to pay for it. By putting in more thermal energy, the melting point is a proxy for the amount of thermal energy I need to carry out the phase change. So the melting point goes up. So the reason we get a high melting point for compound C for spherical compact molecules is because in melting, I am concerned about disrupting a lattice. The bonds are important. Obviously, the nature of the bonds are very important and so on. And in fact, those things take precedence. The shape is a fine-tuning feature. These are the most important. The shape is fine-tuning. And the shape really only comes in when all the other things are equal. Now, it turns out this is not unique to the hydrocarbons. If I were to look at the melting points and boiling points of this alcohol, the trend would be exactly the same, because it has nothing to do with the nature of the bonds or the number of hydrogen bonds or anything. It has nothing to do with it. It has everything to do with the shape. And the shape manifests itself in the same way. Long stringy molecules, elevated boiling points. Short, compact, spherical molecules, because of disrupting lattices, elevated melting points. So now we have a complete profile of the factors that affect physical properties. King, the bonds. Nature is first, number second. Mass, shape. And it's the interplay of those. So yes, I said first, second, third, yes. But again, it's the interplay of those. So water has 4 hydrogen bonds per molecule. The melting point of water, the melting point of ice is 0 degrees Celsius. Right? But iodine is a solid at room temperature. Iodine doesn't melt, it sublimes, but its sublimation point is somewhere around 32 degrees Celsius. So how is it that a van der Waals bonded compound has a higher, goes to, I'm checking the mass of iodine here, it's 100 and, man, this periodic table doesn't have the mass of iodine, I think it's 127. What is the mass of iodine?
The answer I found is 126.905 atomic mass units.
Thank you. Right, so I can melt water at 0 degrees, that's a low temperature, but to convert iodine to move iodine from a solid takes a higher temperature. And why is that? The molar mass of water is 18 grams per mole, iodine is 254 grams per mole. The mass, right, the mass factor beats the nature and number of the bonds. So you always want to bear that in mind. It's the interplay of those many factors that determines the outcome. Okay, so the last thing we look at is solubility. And solubility is a little bit, in a sense, a little bit different, I guess, from the others. And the way we want to look at solubility is, again, to have a sort of molecular perspective of what happens when A dissolves in B. What happens when solute goes into solvent. Well, let's imagine I have A, and A is my solute, the thing that dissolves. And let's make this my solvent. That's my solvent. So I'm going to dissolve A in B. And there's usually more solvent than solute. So when I get a solution, what does that look like? A will be surrounded by B's. Okay? And that will extend further and further and further. In other words, when the solute dissolves in the solvent to give the solution, from a simple-minded perspective, and this is pretty much true, I am going to break my AA bonds, break my BB bonds, and make AB bonds. Right? So fundamentally, the dissolution process involves the cleavage, the breakage of the solute-solute bonds and the solvent-solvent bonds, and creates solute-solvent bonds. Okay. For that to happen, the energy released when the AB bonds form must be enough to compensate for the breakage of the AA bonds and the BB bonds. So if the solute-solvent bonds do not release enough energy to break the solute-solute and solvent-solvent bonds, A will not dissolve in B. Put another way, B will not allow A to dissolve in A. So the decision for dissolution to happen is made based upon the relative energetics of solute-solvent bonds and the solvent-solvent, solute-solute bonds. If the energy released when I form solute-solvent bonds is enough to break the solute-solute and solvent-solvent bonds, all is happy and well, A will dissolve in B, and we get a solution. If the energy released is not enough to break these both, there will be no solution. So whether something dissolves in something else is a question of energetics. Now, let me just put the disclaimer. This is about 80% true. There are other factors that are involved. Entropy comes into play, and a couple other factors. But energetics plays by far the biggest role. And so that's the one we're going to work on. It's about 80% true. But if I tell you there's an 80% chance it's going to rain tomorrow, I'm going to carry an umbrella. If I tell you there's an 80% chance you're going to win the lotto if you buy a ticket tonight, you're going to buy a ticket. Right? So we're happy with 80% of the argument. Okay, so let's see how it works. Well, let's pick our friends hexane and water, shall we? So let's say my solute is hexane, and my solvent is water. So I'm going to ask the question, does hexane dissolve in water? Well, I don't know. Should it? Well, let's see. What kind of bonds would I form between a water molecule and a hexane molecule? What kind of bonds form between a water and a hexane? And the answer is van der Waals. Van der Waals bonds exist between anything with mass. Remember how important mass was in our understanding of the van der Waals argument? There are van der Waals bonds between anything with mass. So between a sodium ion and a chloride ion, there are two types of forces. There are the ionic bonds, and then there are the van der Waals bonds. Between water and water, hydrogen bonds and van der Waals bonds. Between hexane and hexane, van der Waals bonds. Between hexane and water, van der Waals bonds. But if I'm talking about the bond between sodium and chloride, I don't mention van der Waals. If you have two jobs, and one pays you $1 million a year, and the other one pays you, $10,000 a year, yeah, you don't talk about a $10,000 job. I mean, it doesn't count. But if the only salary you make is $20,000 a year, well then that's what you're talking about. That's your salary. So the only time van der Waals forces are discussed are when they are the only game in town. So van der Waals forces exist between anything with mass. So the bonds between water and hexane are van der Waals. What are the bonds between hexane and hexane? What are my solute bonds? Well, they're van der Waals. What are the bonds between water and water? Well, they're hydrogen bonds. So will hexane dissolve in water? Well, let's see. The energy released when the water-hexane bonds are van der Waals, that's the same amount of energy I would need to break the hexane-hexane bonds. So hexane is a go. Hexane is giving up weak van der Waals bonds to make weak van der Waals bonds. That's exchanging pawns in chess. That's fine. Hexane, therefore, is all in. Hexane doesn't mind dissolving in water. Okay, good. Check that box. The bonds between water and water are hydrogen bonds. Hydrogen bonds are strong. The energy released when the water-hexane bonds are formed will not be enough to break the water-water bonds. Therefore, the water lattice will not open to receive the hexane, because I'll be replacing strong stabilizing bonds by weaker, less stabilizing bonds. So although the hexane is perfectly content to dissolve in the water says, no thank you. So there is no dissolution. Because dissolution has to be a mutual agreement between the solute and the solvent. They both have to get out of it what they put in, right? The energy released when the bonds form must be almost the same, if not better, as the energy in the individual units, the stability in the individual units. So hexane does not dissolve in water. I could have flipped it. I could have made water the solute and hexane the solvent, but the same thing would be true. The water-water bonds, the water-hexane bonds in the solution would not have broken the water-water bonds in the solute. So water would not have wanted to split apart to go into the hexane. The hexane would have been perfectly content with it because it's exchanging van der Waals to van der Waals, but the water would have nothing on it. What if I change my solute to methanol? Will methanol dissolve in water? Well, what are the methanol-methanol bonds? Well, those are hydrogen bonds. And what would the water-methanol bonds be? Well, those would be hydrogen bonds. Right? So the water-methanol bonds would be hydrogen bonds. So the energy released when the solute-solvent bonds form is of the same order of magnitude as the solvent-solvent bonds and the solute-solute bonds. So as those bonds begin to form, I release enough energy to break these, so the dissolution happens. So methanol dissolves in water, quite merrily. That's another point. Methanol dissolves in water so well that we say it's miscible. What does that mean? I mentioned this to you guys once before. Miscibility is infinite solubility. So normally, yeah, we did talk about this. If I try to dissolve salt in water, and I have a glass of water and it's a colorless glass, I can add salt and stir, and the first 3 or 4 spoonfuls of salt will go in and it will all dissolve and there will be no solid, no separation of phase. But then a point comes after my 6th or 7th spoonful where I see salt particles at the bottom. There's a phase separation. So salt has a limit to solubility. It's soluble, but it has a limit. If I take that same glass of water and I put in tablespoon after tablespoon, gallon after gallon, barrel after barrel, ocean after ocean, I will never see a phase separation. So methanol dissolves infinitely in water, never have a phase separation. So infinite solubility is called miscibility. Okay. So ethanol is miscible in water. So methanol is miscible. Ethanol is miscible. Propanol is miscible. But by the time you get to butanol, pentanol, they have a solubility, but there's a phase separation. So why is that? And then by the time you get to hexanol, it's essentially insoluble. So what I'm seeing is that when I go from methanol and ethanol and propanol, these are miscible. Butanol we call soluble, and I'd say pentanol, 2, 3, 4, 5, pentanol and hexanol and so on, these are essentially insoluble. So what the heck is happening there? I mean, after all, these all have hydrogen bonds. These are all hydrogen bonding compounds. And I just made the argument, look, what are the bonds between hexanol and hexanol? They're hydrogen bonds. The bonds between hexanol and water should be hydrogen bonds. Between water and water are hydrogen bonds. So they should exchange bonds, they should dissolve. We're not seeing that, we're not addressing that. But there's a pattern here, right? With a small number of carbons, my solubility increases. Or put another way, as the number of carbons increases, my solubility in water decreases. Now, for example, if my solute was butane and my solvent was pentane or something, will butane dissolve in pentane? Let's see. The butane-butane bonds are van der Waals. The pentane-pentane bonds are van der Waals. The pentane-butane bonds, van der Waals. So yeah, butane will dissolve in pentane. Energy release, when I form van der Waals bonds, enough to make the van der Waals bonds in butane, my solute, pentane, my solvent. No problem. So why is it, as the number of carbons increases, the solubility in water drops? Well, if you think about it, what happens when I put an alcohol in water? Well, the waters will associate a hydrogen bond with the H's, with the alcohols. So the alcohol will hydrogen bond to water. But I've only drawn the bonds that are happening at the OH end. The alkyl group is an entity unto itself. Now, there'll be a slight delta plus charge in the R. Well, not a slight, a significant delta plus charge in the R. And there will be a dipole-dipole bond between the O and, I'm going to put a different color. There'll be a dipole-dipole bond between the O and the R. But that's going to pale in comparison to those. This would be dominated by hydrogen bonds, as long as R doesn't get too big. So when R is just methyl, when it's just one carbon, well, you know, I've got a dipole-dipole bond between that carbon and the water. And what you have to recognize is what this water is giving up. That water molecule is giving up hydrogen bonding to its neighbors to form a dipole-dipole bond with the alkyl group, with the carbon of the alcohol. So this water is giving up a hydrogen bond for a dipole-dipole bond. But that's okay. It might just be one or two water molecules doing that. The rest of them are happy with the hydrogen bonds. Enough energy collectively is released. But when this becomes 2 carbons, 3 carbons, 4 carbons, 5 carbons, you are now immobilizing more and more water molecules along a hydrocarbon tail, where not only are you no longer forming dipole-dipole bonds, you're now looking at van der Waals bonds. Because you see, this carbon right here has a delta plus charge. So the water molecules that are close to it, right, I'll have a dipole-dipole bond here. But there's basically no dipole on these carbons. You're now stuck with van der Waals. So at some point, you get to a place where, even though you're forming hydrogen bonds on this end, and maybe some dipole-dipole bonds here, by taking a lot of waters out of solution, away from their strong stabilizing hydrogen bonds, and telling them instead, make van der Waals bonds along the chain, at some point the energy release from the 3 or 4 hydrogen bonds here and the van der Waals bonds here doesn't compensate for losing the hydrogen bonds in water. And when it is no longer favorable, it stops and it no longer dissolves. So as your carbon chain gets longer, your aqueous solubility drops like a stone. And in fact, what you find is if I have one OH or NH2 This is true as well, because that also forms 3 hydrogen bonds per molecule. If I have 1 OH or NH2 for every 3 carbons or less, I am miscible. 1 OH or NH2 for 4 carbons, maybe 5, you're soluble. But if you have 1 OH for more than 5 carbons, you're no longer soluble. And here's the beautiful thing. If I take hexanol, hexanol is not soluble. But that is, because now I've got 1, 2, 3, 4, 5, 6 carbons for 2 OHs. I'm down in 3 carbons to 1 OH. In fact, that is probably darn near miscible. That's somewhere between soluble and miscible. So if I have 1 OH or 1 NH2 for every 3 carbons, I am miscible. 3, 2 carbons, I'm miscible. 1 OH for more than 5, for 5 or more carbons, and I tend to be insoluble. Certainly more than 5. I tend to be insoluble. 1 OH for 4 or 5 carbons, I'm in that soluble range. And it's we're talking about aqueous solubility now. And it's a question of energetics. It's literally a question of energetics. Okay, we stop here, but there's a question I need you to ask. I need to ask you, and you think about it as you answer. I will pick this up in the next lecture. And here's the question. We have made the point that solubility is a question of energetics. That the energy released when we make the solute-solute bond, the energy released when we make the solute-solvent bond must be enough to compensate for the breakage of the solute-solute bond and the solvent-solvent bond. Excuse me, 1 second. Right. So, I apologize. So, ionic compounds, yikes, have the strongest, ionic bonds are much stronger than hydrogen bonds. So tell me, why is it that ionic compounds dissolve in water? Right? The ionic bond is much stronger than the bond between a sodium ion and a water molecule. Right? Or between a chloride ion and a water molecule. Right? These bonds, by the way, are called ion dipole bonds. The bond between an ion and the dipole is called an ion dipole bond. And ion dipole bonds are much weaker than ionic bonds. And they have to be. Because the charges on these are much larger, right? The force of attraction depends upon Q plus and Q minus. And although Q plus here is large, Q minus here is small. Q minus here is large, Q plus here is small. Okay? That being said, how is it then that ionic compounds dissolve in water? When the energy released when I form a sodium water bond and a chloride water bond is not enough to break a sodium chloride bond. I want to put it another way. When I take sodium chloride and I dissolve it, what I do is I literally break up the lattice. Sodium ions, right? What that gives me when I add water is aqueous sodium ions and aqueous chloride ions. And they're swimming away in solution. I broke the lattice. I could do that at room temperature. I can do it with a glass of ice water. So at 0 degrees Celsius, I can stir salt into water and break up the lattice. at 0 degrees Celsius. But if I take the same solid salt, the melting point of sodium chloride is about 1500 degrees Celsius. And that gives me molten sodium ions and molten chloride ions. It takes me 1500 degrees worth of heat to break up that lattice. That's a massive amount of energy. Or, guess what? I could stir it in water at 0 degrees and break up the lattice as well. So my question to you is, how is it that ionic compounds with strong ionic bonds dissolve in water when the ion dipole bonds are too weak, release too much energy to break the sodium-sodium bonds, the sodium chloride bonds? What is water doing that it can facilitate the destruction of the ionic bonds that require temperatures in excess of 1000 degrees to do the same thing? Okay? So think about that for the next time, and we'll pick up the next lecture there. I apologize for the full